gents, back we are again. What we're going to have a look at now is justifying and showing through some fairly simple calculations why we transmit electricity around the country at high voltage. So there are a range of reasons. So starting off with this activity, why do we distribute electricity at high load? For a typical load on a distribution transformer of 500 kilowatts, carry out the following calculations. Calculate the current to service for that load at 400 volts, yeah, and calculate the current to service that load at 11,000 volts. And we'll look at the difference, yeah, and we'll consider the implications. We'll do that bit first and then move on to the next. I'll do this in stages, I think. So 4 or 5 minutes, see if you can do those calculations. Right, so what's the version of power formula we need to use here? Yeah, we're using the P equals IV, which we rearrange to I is equal to P over V. So in this 400 volt case, we've got 500 times 10 to the 3, because that's kilovolts, divided by the 400 volts, and the answer is lots of amps. How many? 200 and what? Yeah, 1250 looks more like it to me. Yeah. And then calculate the current to service the load at 11,000 volts. So again, where I is equal to P over V, same power, 500 times 10 to the 3, divided by 11,000 equals 45 amps-ish. Yep. So, what do you think are the implications of those calculations? What's wrong with yeah, that's actually that's looking at what we're going to do on the next page in a way. Think about the amount of current we're trying to pass through the cables. Yeah. What does more current mean in terms of the cable? You have a bigger cross-sectional area. Yeah. So if we were trying to hang cables to take 1,250 amps on the pylons, be too big and too heavy. Most of those cables, a lot of them are aluminium conductor, but with a steel core for strength. Yeah, so they're gonna. The bigger you go, the more weight you got to hold up on the pylons, the harder they are to get up there, and so on and so on and so on. So the more current we have, the bigger the cables have got to be. So there's a valid reason for increasing the voltage, because it reduces the current. So at low voltage, larger CSA. Are you alright with me putting CSA for cross-sectional area? Cables. So that's the main issue around, or one of the issues around the current. Yep. But it also leads into what Ryan was saying here, that's on the next page, about power loss in the cables. Yeah, because whilst a piece of copper or aluminium cable is relatively low resistance compared to any load that you put on it, it still has some resistance. Yeah. So looking at the next page, bearing in mind we want to use the two results we've had on the previous page, the 1250 amps and the 45 amps. If we assume that a long cable run means that a single power cable has the resistance of 0.5 ohm. These are not typical figures, they're not anything I've found out, that's just suppose that a cable run's got 0.5 ohm resistance. Yeah. Calculate the power loss for the cable at the currents for both 400 volts and 11 kV. So using the two currents you've calculated, calculate the power that would be dissipated in that cable if you fed it at 400 volts and if you fed it at 11 kV. So what value, what formula do we need for power? We're going to calculate the power loss for each of the two currents we calculated and for that resistance. So we want and you often see textbooks, you'll hear engineers talking about I squared R losses. Sounds complicated, but all it is power loss. Yep, and they're trying to sound more technical than it actually is. It's power loss in cables and in other systems. Unwanted wastage of power. So I need to calculate P equals I squared R for the 1250 amps and for the 45 amps. So in this case, at 1250, so we take 1250 amps, square it and multiply it by 0.5. What do we get? 781,206. So our 781 kilowatts. Yeah. A lot. 45 amps, 45 squared times 0.5. There or thereabouts, is that what it is? Everyone agree with that? More or less? Yeah? So I'm sure you'd agree that that is a very significant and valid reason for wanting to put voltage up and keep current down. Yeah? Much less reduction, a considerable reduction in power or I squared R losses. Yeah? So again, we've now got two reasons: keep the size of the cables down, keep the power loss down. Third thing to consider is volt drop. So every cable used in electrical installation would have a resistance. Typical 2-wire cable resistance representation shown below. So we are two conductors, each of 0.05 ohms. Yeah. Calculate the volt drop for the 411 kV currents. So again, I'm going to use the current and say in the first instance 1250 amps is flowing in there, and alternatively when 45 amps is flowing, assuming that a load is connected. Yep. So we got two resistances of 0.05 ohms. So RT is equal to add the two together. Yeah. At 1250 amps, volt drop, the total volt drop is equal to, V is equal to I times R, 1250 times 0.1, 125 volts. So we'd lose half of that across that top cable length, 62.5 volts dropped, and 62.5 volts dropped on the bottom one. That's out of 400. So out of our 400 volts we're using, 125 of them be dropped across the cables. To the current, what I've joined them together, so you only have to do one calculation. But what you do is say you've got 1250 through 0.05 that give you 62.5, but then you're also going to drop 62.5 on the return track. Once your load is connected, yeah, and that load is going to draw that amount of current, but the problem is you put that amount of current through. It's just an exercise. There's nothing real about this, just to show that if your current is high, you're going to drop voltage in your cables, and that wouldn't be allowed. There's a minimum. I can't remember whether that's 2.5 or 6% maximum voltage drop. Yeah, they are, because you've got a load connected there. Yeah. So to that current, they're in series, because all the current that goes down the top line has got to come back along the bottom one. Yep. Yeah, what the tables for cables have got is an indication of a volt drop per amp per meter. Yeah. So you can when you're doing your design, you can calculate what's the maximum current you want to flow, times by the length, times the volt drop per amp per meter, tells you what volt drop you're going to get, and then there is a limit. But I've been out of contracting so many years, I can't remember whether that's 2.5% or 6, but it's quite low. It's certainly a lot lower than losing 125 volts out of 400 volts. Yeah. However, at 45 amps, volt drop is I times R, which is 45 times 0.1 equals 4.5 volts. And I don't think we'd worry too much about losing 4.5 volts out of 11,000. Yeah. The way they deal with variations in voltage levels is that the transformers have got different tap-ins on them. So they can, the further they are down the line, they can select a different tap-in to keep the voltage right. Yeah. So another reason then for higher voltage where you're delivering a lot of power in electricity terms over distance is that you're reducing the volt drop you'll get in the cables as well. That's all related to how much current's flowing. Alright, so higher current is the general reason, and the three consequences of the higher current is that you need bigger cables, you're going to get more power loss. I mean, because of the squared term, double the current, you get 4 times the power loss. And also, because you increase the current, you get more volt drop for a given resistance. Yeah. So, I don't know if any of you have ever been through that and considered that like that before, but they are 3 valid reasons for keeping the voltage up when you want to deliver lots of power. Yeah. So, 3-phase star connected systems. So remember from the network diagrams, you had delta transformers that were delta delta, and then the last, right at the end of the line, you had a delta primary, and we're going to do transformers in a bit more detail probably week after. But you've got a delta star for the last one, because it brings us down into this star connection that gives us the 4-wire dual voltage. Alright, so 3-phase star connected system. In the UK, the output from the distribution transformer is connected in a star formation as shown. So these 3 arrows here represent your 3 transformer windings, okay, and they're drawn 120 degrees apart to conform to evenly spaced around a circle. Yeah. So we've got a voltage EA, a voltage EB, and a voltage EC. Okay, and we'd talk about line voltage being the voltage between 2 lines, like so. So we've got 3 lots of line voltage. But it produces a dual voltage system, because as well as line voltages, we've got 3 different lots of phase voltage between line and neutral. So a neutral conductor, a 4th wire, is taken off the centre point of that star connection, and that way we get a dual voltage system. Alright, and I'm now going to go through the detail of how that works. Alright? So, the relationship between line and phase voltage for a star connected system. If you think about these 3 voltages at the transformer, each being 230 volts. Those 3 phases are all 230 volt RMS, okay? They're 120 degrees apart in terms of angle. Alright? Now, if you consider a line voltage E line, that's between 2 of those phases. So we've got a voltage here, across there, right? And we've got 2 voltages here, one that way, arrow pointing upwards, clockwise, arrow pointing that way. So that's clockwise, that's anti-clockwise. Who's never heard of Kirchhoff's voltage law? Remember that from science? Yep. What Kirchhoff's voltage law says is that around any one loop, so there's a loop, a voltage loop of 3 voltages. Okay? And it says that all the clockwise voltage arrows will add up to all the anti-clockwise arrows. Alright, so this line voltage can be calculated from EA minus EB. You have to be careful about how you put a volt drop arrow on your diagram. Alright, but in a way that's arbitrary, but I would say that that's the positive terminal, because we always talk about neutral being 0. So you put your arrowhead towards the more positive terminal. Yeah? So I've got that arrow going up there and pointing that way. This arrow's pointing this way. And this one I've chosen that to be the more positive side. But it doesn't really matter. So if we look at this in terms of clockwise arrows, we've got EA. Okay? That's the only one, isn't it? Because I'm saying if we look at the arrow, that's pointing in a clockwise direction. This arrow, that red one. In terms of that loop around there, think of that loop around there, it's pointing in a clockwise direction. Yeah? This one is pointing in an anti-clockwise direction, so we say that's equal to E line. Yeah? And this one is also pointing in the clockwise direction, so plus EB. Do you all agree with that or not? Yeah, but think of it in terms of a loop around a circuit. Let me see if I can help by making a new slide. That might be. Right. Here's EA. I'm going to put a load on the circuit. There's a wire through a load. Okay. Back along this way. And I'll do it in a different colour. There is EB. Alright, and both of those, if that's considered to be 0 volts, both of those, that's considered to be pointing towards the most positive terminal, 230 volts. Yeah, that's pointing towards another 230 volts. This 230 volts has a 120 degree angle associated with it. Yeah. And then here, what's our load? Do it in blue. We've got E line. Yep. So that's isolated loop, the circuit loop that I'm talking about. So that's your resistor as a load, okay, and a current, I'm sure you'll agree, would flow in that circuit, and that's AC anyway, so it's going backwards and forwards, but we'd put a current arrow on at a certain time going that way. We've got a loop here in this circuit of voltages around it. Think of it like a circle. Now can you see that arrow points clockwise around that circle and is the opposite direction to those two arrows in terms of that loop. Yeah? So the way I always teach Kirchhoff's voltage law is put all the clockwise arrows on the left-hand side. So we say EA, and that's the only clockwise arrow. And it's equal to EB plus E line. Yep. I'm trying to find E line. So how do I make E line the subject to that formula? How do I make it E line equal something? What do I need to do to that side to make it E line on its own? Subtract EB, yeah? So we can say E line is equal to EA minus EB. Agreed? And I believe that's the formula for E line that I've got on the previous page. E line is equal to EA minus EB. Yeah? So what I'm trying to show you is where the two different voltages come from. Because the output of the transformer has given me 3 lots of 230 volts that are all 120 degrees apart. So we'd say perhaps that this one is plus 120 degrees. If we do that, then the other one is minus 120 degrees. Alright? What we can then do is draw a phasor diagram. So I've done that over here, and I'll the red one there, EA, pointing straight upwards. Okay. Here's EB, that's the positive EB, and there. So if I want, and that's drawn at 120 degrees from that one. If I want minus EB, I go in the opposite direction. So there is minus EB. If we drew this to scale, you'd be able to see this working. Alright, what we then do is complete the parallelogram between those, alright, and the resultant, those two added together in that formula, or one subtracted from the other, is equal to that blue line up the middle. Okay? We then consider a little piece of geometry and some sine rule to calculate what the line voltage is, considering the other two at 200, considering their angles. Yeah, so if we look at this triangle here, yeah, in isolation. So when you label this up, sine rule is this line length against that angle. So we can say EL over sine 120. This angle in here has to be 120 degrees. Yeah? So sine rule EL over 120 is equal to the phase voltage over the 30 degree angle. Yeah? Using sine rule. Anyone not see that? Rearrange that formula. So we want to find EL. So we multiply both sides by sine 120. We get EP sine 120 over sine 30 over that side. If you do sine 120 over sine 30 on your calculator, making sure you've got your calculators in degrees, you'll find, hopefully, that gives you the result of the square root of 3. Yeah. Hopefully, if your calculator is set up to show roots as roots and not as a decimal number. So, in a star connected system, the line voltage is equal to root 3 times the phase voltage. So if you in your calculators put 230 times root 3, you should get 400. 39 odd. Yeah. And you'll notice that phase voltage is 30 degrees out of phase with each of the line voltages that make it up. Yeah. Alright. Anyone completely confused by that non-right angle triangle trigonometry? We should have covered sine rule in maths. Yeah. Here's EL. There's EL of 120. Right. There's EA. There's EA of a 30. You can say those two ratios are equal to each other and then rearrange to find the unknown, which is what I've done. And it wouldn't matter which two of those phases I chose, I'd get the same result, that EL, the line voltage, is equal to root 3 times the phase voltage. Equally, if you know the line voltage, you can divide that by root 3 to get the phase voltage. Yep. So, having looked at voltage, what about current? Well, if we call this the line current, travelling down this line here, each load is also getting all of one of the line currents. So the phase current and line current in a star system are the same. Yeah? So if you, just by looking at the diagram, you can see that all the current travelling down one line is going to go through the load connected to that line, get to the star point, and return down the neutral to the end. Yeah. So the two currents, line and phase current, in star connection are equal, same. Right? And if the load is balanced, you can show with some complex number mathematics that you can add all the three currents that travel down the neutral together and they actually add up to nothing if the load is balanced. Okay, so if you've got a perfectly balanced load and you put an ammeter in the neutral, you get no current. But if you unbalance it, you're going to get some current in it then. Alright? Because Kirchhoff's current law says all these currents add together to make one big current down the middle, but because they're out of phase with each other, the angles cancel them out. You try and balance the load, yeah, because three-phase loads normally, like motors, will automatically present themselves as a balanced load. As when you start to get single-phase loads, if you're not careful, you put too much on one phase, you'll end up with an imbalance. You end up with a neutral current. Too much neutral current's not necessarily a good idea. So the supply authority will try their best to balance a load. So where you've got a big housing estate, if you ever lose one phase, you'll see every third house has lost their power because they try and go, yeah, brown phase, blue phase, grey phase, brown phase, black phase, grey phase it is now. Still ain't got used to them new colours. Red, yellow, blue used to be in the olden days. Excuse me. My bungalow where I live, because originally I had underfloor heating and now got storage heating, I got three-phase to my bungalow. Because that's a remote area, that heating load is over 3 phases. So that I don't present as a big load on one phase. Yeah. Alright. So that's a 3-phase star connected system. if you're supplying a motor and are star connected, you don't connect that middle neutral line, you leave it. Yep. But if you're connecting 3 separate loads, a 3-phase heater bank or something, then you would normally connect the neutral. Yep. Alright. And you get, for the same resistance load, you get different power outputs between this and the delta that we're now going to have a look at. Alright. Incidentally, generators are usually 3-phase generators, invariably connected in star. Don't connect them in delta. Right? Because what happens is, if you get an imbalanced load in a generator connected in delta, you get currents that flow just round and round the windings in the generator, causing heat and doing no real work. So, next page. Relationship between phase and line current for a delta connected system. So, if you look at a delta connected system, there's no neutral, just 3 wires, and each of the loads has got the line voltage across it. Right, more about that in a minute. But if we look at these currents here, IA turns into a bit of I1 and a bit of I3. Yeah. So in delta, it's line and phase currents that are different. Because these two are going to be a little bit less than the IA flowing in there. These two are each going to be a little bit less, but add together to make up IC. And these two, I1 and I2, make up IB, for instance. What you must remember is that everything in this circuit is constantly changing as the AC 50 cycle sine wave goes through its process. All 120 degrees out of phase with each other. So here we've got 400 volts, and if that one's the 0 degrees one, we got another 400 volts, 120 degrees there, and we got a further 400 volts angle minus 120 degrees between the other 2 phases. So again, we get a very similar phasor diagram, but this time in terms of the currents. Yeah. There's a line current and a phase current in there. We've got that triangle back again. But we got IL of a sine 120 is equal to I1 of a sine 30. We rearrange that to IL. We got this 120 of a sine 120 of a 30 again, which turns out into root 3. So the line current is equal to root 3 times the phase current. Or the phase current is line current over root 3. So in delta, the currents are different, voltages are the same. Each phase gets the same voltage, 400, 400, 400. Yep, that's the line voltage. Happy with that? Yeah. So, in final summary, the 2 different systems side by side. In a star connected system, each phase sees a voltage of 230 volts. Each load passes a phase current that's equal to the line current, and for a load that includes a neutral, there will be no neutral current for a balanced load. In the delta connected system, each load in each phase sees a line voltage of 400 volts. Each load passes a phase current that is equal to IL of a root 3. Yeah? Alright? And you'd get different powers for the same resistance load out of the 2 systems. Yeah, that's the idea is running current really. Once you've got to start, because if you start in delta, you're going to get a bigger starting current than if you start in star. Yeah, because you start in star, you've got 230 volts across each winding. Then once that's run up a little bit, you start to build up some back EMF because the windings inside are interacting with the magnetic, the magnetism in the stator, so you get some back EMF. You know, if you watch a dynamic, you start a motor, it whacks over, doesn't it, and then settles down again. Well, then if you switch over to delta afterwards, you're then getting 400 volts a phase because you're in that mode. So you're starting in that mode, 230 volts across each winding, so you limit starting current. And once that's wound up and you've got some back EMF, you then switch into delta and you've got 400 volts per winding. So you got more power. Yeah. One thing we had on a machine at Fibronile was big hydraulic pump, probably 100 horse motor. And when you start this hydraulic pump up, it started up in star, and then when it changed over to delta, we were getting like a big reaction to that on its rubber mountains that was actually clanking up against the framework of the machine, and that was dimming like the control lights on the machine. Because what you mustn't do is obviously have the star and delta contactors in together, because you get dead short across phases then. So you have a little timer that drops out the star and then a short time later brings in delta. The reason for that we eventually found, because what the Japanese people said, well, they were going to give us some different mountings, so that was mounted higher and weren't going to clank on the side of the machine. That was their solution to the problem. What we discovered was the delay time between the switchover was too long. So the motor was running up to speed, then when it switched out of star, it was slowing down again, and then when you switched into delta, you were getting a second starting current and a much higher starting current. So reduced that time, no problem. So we will probably cover star delta. I'm not sure exactly what's in the spec, but there needs to be a delay between the what's called the star contactor dropping out and the delta contactor coming in, but not too long. If it's too short, you'll get dead short cross windings. If it's too long, the motor will run down speed, and then you get a second starting current. Alright, but that's gone a little bit off our beaten track for today, but that's an explanation anyway. Alright, and have you three-phase motors on single phase? You need to really be sure that they can be and so you get 230 volts per phase. So you have to watch that, and you need to have they found out, you know, they could run these little conveyor motors off single phase 230 volt. Yes, you can, but they need to be the right motor. Okay, moving on again. Earthing system. Right. The power authority at the distribution transformer connects the star point of that winding to the mass that is Earth. Yeah. Now, they often get asked, why do they do that? Okay. Because it causes all these problems we have with Earth fault loops and so on. But if we go back to our star connected system, where we got all three, if we don't tie that down and make that a solid 0 volts, if the load is imbalanced, it would mean that the voltages between neutral and phase would float. So you wouldn't have 230 volts each on every phase. You'd get one phase with 200, another phase with 250 for instance, and the third one with 230. And they would float around as the load on each phase changed. That's impossible for them to perfectly balance the whole country as a load. So they do this. As I've seen, they do that. What that however means is, if we take a route through a circuit, so here's an appliance over here with a metal case. That's the fuse for the circuit. There's the load through a neutral bar and back to the star point. We get a fault to that metal case that puts that metal case at 230 volt potential. You walk up to it standing on the ground, and that gives a path through you back to that earth point, and you get a shock. That's why my man's got hair sticking up on end. Yeah. So it's a very basic look at it, but that's the danger. Yeah. So because of that, and incidentally I'd expect some of you to know, how much current passing through your body is enough to kill you. Let's go around the room. What do you reckon? How many amps? Have a guess. 10? 1 amp? 1 amp? 3 amps? 2? 300 amps. Yeah. My gentleman over here is actually correct. That's 50 milliamps, 0.05 of an amp. Yep. It does have to do with voltage levels, because for your given body resistance, a higher voltage is going to push more current, but it's the current level that kills you. Okay. And 300, you'd be scraping a lump of carbon up off the floor. That's all that would be left of you. And I don't say that to make fool, because I do that lots of times, and I get currents between usually 2 or 3 amps and 500 or 600 as I go around a class. Yeah, but it's 50 milliamps. Hence the 30 milliamp tripping current of the highest RCD there is. Yeah, and then they go down from that, don't they? But more about that when we look at safety devices. So it's just worth bearing in mind that don't take a lot of current to kill you. All right. I don't know if you've seen in the news, but people have been killed by putting their tongue on 9-volt PP3 batteries. Not a good idea at all. Yeah. Well, of course it can, because different bodies going to have different resistances. So are you willing to test that? Yes. I mean, up here, across here is worse than down there. I don't know, I ain't got a clue. I haven't got a clue. Yeah. Yeah, but they need to put enough voltage on to get that current to flow, and hopefully they want to do it quick. They put some dampness between you and the electricity as well. Yeah. But watch the Green Mile if you want to see what happens if you don't put the water underneath the cap. Anyway, we digress again. This issue means, well, hence, because of that, there's a need to provide an alternative path for any earth fault current. Yeah? This issue means there's a need for an earthen system to protect against shock from the metal case. Alright? So, earthen arrangements. 5 types of earthen arrangement. They describe the way the installations are earthed. TN-S, TN-CS, TT, TNC and IT. The first 3 are the arrangements we generally use. Okay, if you're someone who's done even the 17th edition regulations course and more recently the 18th, you're probably going to know more about this in depth than I do, because I've been out of contracting a good long time and I haven't done those courses. Alright, the first 3 are the ones we generally use. The last 2 do not comply with the supply regulations and therefore cannot be used on public supplies. They can be used privately, but sometimes they have to get permission to use them, and are used in specialist situations. One of them is used in hospitals where you don't want that supply to go off because that's keeping somebody alive, and so you do something else to reduce the danger for people. Yep. Okay, so I'm not looking at those 2 in detail, I'm only looking at the first 3 in detail. So, TNS system. In this system, the neutral and earthen arrangements are separate throughout the whole of the system, on both the supply and the consumer side. So here's the cable coming in. There's the live going up through the meter, the neutral going up to the meter, 2 tails to the consumer unit, and the earth is separate as a main earthen terminal and going to your main earthen terminal in your consumer unit, and the earth and the neutral are separate for the whole installation. Yeah. So looking at that in terms of fault current, there's the transformer winding here. Here's our fault current flowing through the protective device, through the fault to the case, down the earth cable. There's the main earthen terminal. There's the sheath of the cable to your house, so maybe a steel wired armoured or a cable with its own earth in it, back to the centre point of the transformer. Alright, and there's that stake in the ground. So we've got a path through that cable back to there, and you would hope that that would cause some kind of protective device to trip, but more about that later. Okay, but the key thing in here is that this path here has low enough resistance to cause the protective device to trip. And again, more about that soon. Alright, so TNS means neutral and earth. Terra is earth, neutral, separate. That's what the letters stand for. Alright. And there's a third diagram that kind of shows it in terms of a house. There's the transformer, line conductor, neutral conductor and protective conductor all separate, all the way to the user's consumer unit. Alright. All happy with that? TNCS, Terra and neutral combined separate, is what those letters stand for. Here, the supply cable has the earth and neutral combined in one conductor. In most instances, this is the arm and the cable. The only difference between this and the TNS system is the earthen arrangement at the intake point. So, what they do is combine earth and neutral at the incoming point and then that earth is connected to your main earthing terminal. However, if we look at the next diagram, well, no, that's the third diagram that shows this. So here's the path for the fault current, is along here, through the protective device, down through the fault, through that earthing conductor, separate earthing conductor in your house, to your main earthing terminal, and then to the board's link, and back down the neutral to there. And again, the important thing is that that path is of low enough trip protective device. Yeah. So the issue in this case is what happens if that neutral is lost anywhere along that line. Yeah. You could still get an issue of get a break in this cable here. Someone standing there with their hand on earth is still going to make this connection through earth back to that point. So what they do is they connect earth electrodes to that neutral cable at several points along its length, and that's why this system is also called or referred to as PME, protective multiple earthing, because when this first came out you had to make sure that they'd done those extra earth stake connections before you could put a system in that used PME. No, that's different to supplementary. Bonding is a completely different issue. But bonding is about making sure that all the metal work in your house can't be at a raised potential, or making sure that you can't have hot pipe at 240 volts, cold pipe at 0, and you grab both of them at the same time and make a circuit. So it's about, there's extraneous metal work and there's supplementary, isn't there? So you've got your case that is part of your installation, your main water supply, but then you've also got, if you go to farm buildings, you've got metal that can storage and all sorts that you need to bond. It's about keeping all metal work at 0 potential, so it can't raise above 0 volts. Alright? Again, that's kind of a little bit out of my field, and we're only touching on it here. If you were going to be an installation person, you'd go and do the regs course anyway, wouldn't you? Alright? So that's TNCS, or another name for it is PME, protective multiple earthing. And that's where the route from the intake inside your house, the bit that's owned by the board, that the meter, so everything after the meter is yours. That's where they connect the earth to the neutral at that point, and at various other points along the line to maintain a better earth is what the intention is, because you've got multiple connections to it. Alright? And the last one is TT system, Terra Terra. In this system, you don't use the supply cable at all for the earth. You've got your meter tails coming into your consumer unit, and you take an earth wire from your main earthing table, earthing terminal, and you connect it to a stake that you drive in the ground, or multiple stakes that you drive in the ground. So if your house is supplied by a direct overhead system at 230 volts nominal, it's unlikely to have a separate earth with it. So you'd put this system in. TT must have an RCD, residual current device. Again, we'll talk about that a bit more when we do safety devices. Alright? But the value of resistance to the earth electrode, so the important thing here is that you drive that stake in and you get a good earth. Because resistance must be low enough so that when you get a fault current travel through it, you don't raise that conductor by more than 50 volts, so you don't get more than 50 volts at this point here. Because if that's of high resistance, you'll start to raise a voltage here that could become dangerous. Okay, so again, that's about doing the calculations and knowing what you've got to get that resistance down to. But if you put one of these systems in and the board come to connect it, and that stake ain't good enough, they won't connect. Alright, so again, general mass of earth becomes the earthen arrangement. You put a stake in the ground, or multiple stakes if you need to make that earth good enough so that it trips and you get enough earth fault current. Sorry? I don't know. I've been out of it so long. We used to put stakes in, and you could screw them together so make longer ones. Yeah. 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 On one of the other pages, there's something about different electrode types. I think I found. So again, here, look, your earth fault path is through here, through there, and that's relying on that stake for a good connection to earth, so it can travel through there and up there. So if that isn't good, and another thing they talk about, this earth fault path is equal to what they call ZE, which you can get from the board for the particular area you're working in. That's the resistance of that path from there to their earthen terminal. You've then got to add that to the resistance of your earth cable plus the resistance of that to find the total earth loop impedance. Yeah. And for this particular installation type, it's typically going to be much higher than it would be for the other two that have got a proper copper cable or a steel armour and being used as earth. Yeah. And on this page, again, showing that that's through a general path through earth. But BS 7671 are the regulations, and they talk about earth rods or pipes, tapes or wires, earth plates. You're talking about them like in grids. So you actually dig a hole, I presume, and put a big grid in the ground, yeah? Yeah. I've never personally installed one of them, but yeah, yeah. So if you're working in that area, you've got to be more familiar than I am. I've been out of that for, well, I've been teaching for 11, 12 years. Along the time I was just a Mr. Fix-It maintenance guy at Fibre and Isle. So, yeah, but so PT is the earth stake system, alright? Yeah. And there is my full references for the two references that I put in the notes. So again, I'm just showing you how we do the Harvard referencing system. So when you're referencing research that you've done in your reports, that's how I would expect you to do it. You put an in-text reference author date, you know, as a company website. So you noticed I had Beardmore R 2012 in the text. That refers to this reference at the end, and then the person can find that in a book or on the web according to that. And whenever that's web, you always have to put last accessed. So if the person reading that can at least, if they can see that's old access, that might have disappeared the time you look at it. Okay? One thing I set up while we were having break that might help show where that 230 and 400 volts come from, and the two guys that I taught before will be familiar. Remember how I used that graphing software in maths, Desmos? Yeah, I'm glad that you do, because that's good. Sorry? You can get an iOS and an Android app that'll run this as well. Start graphing. You can have an account So, and that's easy if you've got a Google account. You just click connect with Google, and that will allow you to sign in. Oh, why is that? Oh. You can save graphs and go back to them. Let's have a look. Should have that. No, it won't let me. If we put in, I'm going to put in the 3 phases, 230 volt. So Y1 is 230 volt sine X. Let's just set this. You can go here and set the, first I want my angle in degrees instead of radians, and I want to be able to see -10 will do up to 400 degrees on the x-axis. Will allow me to see a full wave. Y-axis I want -420 to +420. So there's my phase at 0 degrees. Put in a second phase, Y2, 230 sine X plus 120. So there's a second waveform, 120 degrees out of phase with the first one. Yep. And then third one, Y3, is equal to 230 sine X minus 120. So there's your 3 phases, each at 230 volts. Yep. If I now put in Y4, that's equal to Y1 minus Y2, and enter, I'll get that line voltage that peaks at 400, or 398.372, which is √3 times the phase voltage. Yep. And again, I could equally put in Y5 is Y1 minus Y3, and Y6 is Y2 minus Y3. And I'll get 3 line voltages, each 120 degrees out of phase with each other. Yep. So that helps to prove that maths we did earlier in those phasor diagrams are correct. Yep. Alright. How are we doing for time? Ooh. Got a lot done today. Does it seem like we've done a lot? Do you think that's been too much I covered today? Well, all I can do, yeah, the answer be handy, yeah, know all that. Right, if we look at learning outcome 1, describe the features of an electrical distribution system. Yep. So I'm going to ask you something about components in an electrical distribution system, or that we looked at today. So remember them network diagrams that we did, and what's in there, got transformers and so on. So it's going to be something about you describing the features of what makes up an electrical distribution system. Yeah, yeah. I mean, I'm not gonna. You're at level 4 now, so it's not. I give you write it back to me. You're gonna have to work at it, particularly for the merit and distinction grades. Yep. But in that sense, you know, most of what you're going to need to pass is going to be there somewhere. If you look hard enough, you might have to just look a little bit more. Yeah. Incidentally, your comments, whoever it was who had a chat with the external, regarding the fact that if you don't get the merit on the first blinking assignment, you fall down to a pass, or you don't pass at all. Ain't worth even trying to get the passes later on. I'm kind of with you with that. I can't do anything about it, but I can understand that. Because if I think about my degree course, you've got a module that's got 3 assessments in it, let's say 2 assignments and an exam. You might get 45, or you get a bare pass, 40 to 59 as a pass. Yeah. But you're not completely stymied about getting a merit there, because if you do really well in the other 2, and let's face it, the idea is to improve as you go along. So you get better at academic writing, you get better at the calculations or whatever it is you're doing, and assignment 2 you improve, and you do really well in the exam. You might have only just passed the first one, but you could still got a chance of getting a merit. You only just got a merit, you might chance to get that up to distinction with the other 2 results. Here, you don't get that first blink of merit, you're stuffed. I don't think that's right, but I've got nothing I can do about it. I don't make the rules, but I have to stick to them. So once you haven't got it, you don't get another chance on that. Yes, that's the other thing. You've done all that work. Something happened that you only get capped at a pass on the last assignment, and you're buggered. Again, whether that's fair or not, I don't think it is. I'm kind of with you on it. Having said that, there isn't a lot I can do about it, because the marks on the degree are just percentages. So if you get 40 to 59, you get a pass. If you get 60 to 69, you get a merit, and if you get 70 and above, you get a distinction. And not every assessment is weighted the same, but overall that's what you get. And then your assignment result, your overall module results are all accumulated together again, using percentages and weightings to give you an overall grade for the course. So you can. And the idea is that in students improve as they go along, but this doesn't seem to cater for that to me. Having said that, there's little I can do about it. Alright? So if we're looking at that, I'm going to ask you to do something around describing the features of an electrical distribution system. Yeah? I'm going to ask you to review some symbols. Okay, so it might be that I give you some kind of diagram with some symbols on it that you've seen, and or maybe 1 or 2 that you haven't seen, but you can research and find out what they are, and tell me what they are. Yeah. Explain the different methods of single and 3-phase connections. Yep, we've covered it, or we started to cover it. Yep. Summarise the methods of safe fault finding on electrical distribution system. We haven't done that yet, so we're going to need to look at some typical faults, look at the equipment and the methods you'd use to help you try and find those faults. Yeah. Examine the operation of an electrical distribution system. So that might be something around the way that the distribution system can be switched to maintain supply, and how that operates to supply all the people with electricity most of the time. Yeah. Okay. So I'm not going to major on generation because that's not my background, so I don't know too much about beyond the step-up transformer. I'm not overly aware of what happens in there. I mean, I know a little bit about That's all. That is Harry Potter stuff. Yeah, yeah. Because turn this thing off.